So let's discuss about coplanarity. Now, a system of vectors is said to be coplanar if the supports are parallel to the same plane. Now that means, let's try to understand this problem. So here, let's say we have few vectors, A vector, B vector, and C vector. Now, these three vectors are coplanar. Let's say assume that they are coplanar, then it has to be true that the supports are parallel to the same plane. So we can think of it in this particular fashion. Let's say we have a planar surface, then on this particular plane, all the three vectors are going to lie. Then in that case, we can say that A vector, B vector, and C vector are going to be coplanar. If we want to understand it in a three-dimensional fashion, so let's say this is the tabletop. So here we have these three vectors. So we have A vector, B vector, and C vector. So these three vectors are lying on the same plane, although they look like they are pointing in the same direction, but it is actually from a side view. So here we see that all of these three vectors are going to lie on top of this table, so they are going to be coplanar. The moment if there is a vector which is going to be slightly elevated at some angle, then these vectors are not going to be coplanar. The blue vectors are not going to be coplanar with the yellow vectors. In other words, system of vectors are said to be coplanar if their supports are parallel to the same plane. So that means the support means if we extend the vector in either direction, then these lines must be parallel to the surface of the plane. So in this case, if we consider the yellow vectors, then if we extend it both sides, then their support are parallel to the plane of the table. However, if we consider the blue vectors, so their supports are not parallel to the plane of the table. So they are elevated at some angle, theta. So in this case, here we have theta 1 and theta 2. So we have the blue vectors not coplanar with the yellow vectors. We have visually got an idea how to check whether if three vectors A, B, and C are coplanar or not. However, we also need to verify this analytically. So there is a theorem that is going to help us understand how to check whether if a given system of vectors are coplanar or not. The theorem, which tests the coplanarity of three vectors, tells us that for two non-zero and non-collinear vectors A and B, if any vector R is coplanar with A and B, then this vector R can be uniquely expressed as x times A vector plus y times B vector for some scalars x when y. Okay, now let's try to understand this problem. So here we'll start by first assuming that A vector and B vector are two non-collinear non-zero vectors. Non-zero vector means they both have got some magnitude, and non-collinear means the supports are not the same. They don't have the same support. Or in other words, we can say that A vector and B vector are not going to point in the same direction. So we can consider two vectors A and B such that the initial points coincide. And also they are non-collinear. So here we have two vectors, OA vector and OB vector. So these two vectors are non-collinear as well as non-zero vectors. They have their initial points coinciding at the point O. Now we're going to consider another vector R, such that R is coplanar with A and B. We're going to assume that it is coplanar with A and B. That means it's going to lie in the same plane that also contains OA vector and OB vector. So here we have chosen the vector OP, which is the vector R, such that it coincides with vector OA as well as OB. The initial point coincides, and R vector is going to lie in the same plane that contains A vector and B vector. So here what we have done is we have considered OA vector to be equals to A vector, OB vector equals to B vector, and OP vector equals to the vector R. Next, what we'll do, we're going to form a parallelogram. So we're going to consider PL. We're going to consider PL such that it is parallel to OB, and we're going to consider PN such that it is parallel to OA. So here we have the parallelogram OLPN. Now the whole idea of constructing this parallelogram OLPN, because we need O the vector, OL vector and ON vector. Now what is OL vector and ON vector? So here, as we can see, OL, the vector OL is collinear with vector OA. Collinear means they have the same support, or in other words, we can say they are in the pointing in the same direction. However, OL vector is not equals to OA vector. Here, OL vector is going to be some fraction of OA vector. So, to represent this, what a fraction of OA vector, all we have to do is multiply it with some scalar x, where x is some scalar. Right. Now, similarly, we have ON vector. So, similarly, ON vector is also collinear with the vector OP. So, in other words, we can say similarly, ON vector, it's going to be y times the vector OP. Now, where y is some other scalar. Fine. Now, what we can do, and we can use the parallelogram law of vector addition. So that is going to help us find out OP vector. Now, OP vector, this is simply equals to OL vector added to ON vector. Now, what is OL vector? So we have already defined OL vector as x times OA vector, and ON vector is y times OP vector. And we have already assumed OA vector to be the vector A and OB vector to be the vector B. This is going to be x times A vector plus y times B vector. And also OP vector, we have already defined it as the vector R, which is coplanar with A and B. So here we have successfully expressed the vector R, which is coplanar with A and B uniquely, in a very unique manner. So it has x amount along A vector added to some y amount along B vector. However, when we go back to a theorem, there's a particular word used. It says that it is uniquely expressed. So let us assume that it is not unique. Suppose we are going to go use a contradiction here. Suppose our vector is not unique, and let's say we say that it is represented by x1 A vector plus y1 B vector. Fine. If this is true, then this implies that in place of R vector, we have x1 A vector added to y1 B vector, and this should be equals to x times A vector plus y times B vector. Now, if we rearrange the terms, we get x1 minus x multiplied to A vector added to y1 minus y multiplied to B vector. This will be equals to 0 vector. However, we have already assumed that A vector and B vector, so A vector and B vector are non-collinear vectors. So if they are non-collinears, this sum is only going to be 0 only when x1 minus x equals to 0 and y1 minus y equals to 0, which means that x1 equals to x and y1 equals to y. So that means x1 and y1 are not different things, they are actually the same, x and y. So that means it is true that the vector R, which is coplanar with vector A and B, can be uniquely expressed as R vector equals to x times A vector plus y times B vector. In other words, the theorem can be also expressed as three vectors are coplanar if one of them is expressible as a linear combination of the other two. In other case, we have considered one of the vectors as R vector and we have expressed it as a linear combination of the other two vectors, A vectors and B vector.